Thanks everyone for coming. It's having today. So the goal of this mini course is to give an introduction to a very kind of curious type of structure that appears in different contexts. So these are the so-called Opers or projective structures. Well, projective structures are a special kind of Opers. Just put this in the moment. So these, Opers are kind of very special flat homomorphic connections on the Lagrange surface. We essentially have a representation for vertical origin. They have a collection of special properties. So I'll try to give you an idea where these properties come from. So this is a intro to a special class of homomorphic connections on the surface. Now, what is this special class? Just to give you an idea, for example, for the group GLN, I thought there would be one of these associated with each simple, or if you want, reductive complex Lie group. So these are essentially connections, so homomorphic connections on a, let's say for GLN, on a vector bundle, where the vector bundle has a flag, so if you want a reduction to a maximum to a subgroup, and this flag is not horizontal with respect to the connection, but satisfies a condition which is a kind of Griffith's causality condition, kind of analogous to a condition that comes from Koch theory. And then there's an extra feature on how the connection behaves on the associated gradient. So there's essentially some restriction on the second fundamental form of the connection. So this essentially fixes for you what the associated graded pieces of this vector bundle has to be. And the only freedom you're left with would be essentially the choice of this flat connection. Let's say for GON. Actually, let's say for the case of rank 2, these objects are connections on the first jet bundle of a dual vector characteristic. So if you take the square root of the canonical bundle, take its dual, the first jet bundle of that cal is special connections. Now, these objects appeared actually first. So these objects algebra geometric nature. First appeared in and be traced from to Schwarz. They appeared in work of Gunning in the 1960s. Appearances, let's say, in his work, they essentially the algebraic geometry was not visible. Everything was done in a very in cost cycles and in a very analytic way. And later these objects, so Opers and projective structures, they appeared in the work of Wilhelm Grove, Benson, of course, Frankel, Bensley, Vistas, and so on. And also these special class of connections, they have kind of interesting also symplectic geometric features. So if you consider the modular local systems on your compact, so my surface will be compact, connected, then these objects are kind of Lagrangian subvariety in the moduli Fourier systems with respect to a natural homomorphic connection. So my idea today is a kind of introduction, since I promised an attempt for at least starting elementary. At least we're starting classically. So I'll try to start classically and tell you a little bit about the way Gunning described these objects, which is typically not the way I tend to think about them, and this is not the way you, let's say, if an open works of Biswas or Benz-V, you're not going to see necessarily Opers projective structure described in this way. So I'll start classically today to give you a sort of feeling of the genesis of this, and then maybe, so hopefully tomorrow we'll move to a more geometric view on these objects. So the idea is to start with now with as little machinery as possible. So so essentially what Gunning uses is this idea of Cartan of describing structures in terms of pseudogroups. So Gunning uses Cartan's idea of using pseudogroups for describing geometric structures. By the way, if you cannot see or you cannot hear what I'm saying, just comment at any point. So very briefly, what is this notion? Even today's, I would think it's a kind of considered a bit exotic. So let me just give you a bit of the definition. So reminder. So let's say X would be our actually X could be essentially for starters, X could be just a topological manifold. If you let's say a smooth manifold. So if eventually this would be the underlying surface of our Riemann surface. So let's say this is a smooth manifold, and let's say you consider locally defined diffeomorphisms, right? So if whatever log of X would be just diffeomorphisms that are defined on opens of X. So these are maps on U to V such that U and V in X are open, and F is a diffeomorphism. So think of these gadgets. Now, a pseudogroup is a subset here which satisfies, on one hand, a group-like property and the sheaf-like property. So gamma and these locally defined diffeomorphism is a pseudogroup if first of all it has a group-like property. I'm not going to write this down, but what this means is you can compose whenever you can compose. In other words, if you take two locally defined diffeomorphisms, if the image of one is contained in the domain of the other, the composition, maybe both of them are in gamma, the composition is again in gamma. You can invert whenever you can invert, namely the inverse of a locally defined diffeomorphism is again in gamma. Is again in gamma, and the identity is in gamma. And then there is the sheet-wide property. So gamma satisfies essentially, you don't want, I mean, the full sheaf property. You want to be able to restrict, and if you have a collection of these sections that are so let's see, let me spell this out. So if you have that, let's say whatever f is in gamma, and you have an open inside the domain. The restrictions again in gamma. And then the other condition is that you can patch. So if you have an F in local diffeomorphisms, locally defined diffeomorphisms, and we have a collection, a cover, let's say, restriction of f to each of these ui's is in gamma, then the whole f is again in gamma. Then it is actually in gamma. So if your workout diffeomorphisms are, so you're singling out a special family of diffeomorphisms, and if you can compose them, essentially that's the if you can compose them, and if you can patch them, then you can localize them without losing this property. So somehow Peloton has this idea of classifying structures and manifolds in terms of these pseudo groups, and he actually gave a classification. His view was that pseudo groups should naturally come from differential equations. So differential equations defined from manifolds. And he had actually a classification. He proved a number of theorems on pseudo groups. He had a number of classification results that I'm not discussing. So I think I can give you a reference if you want to trace the connections between between Peloton's terminology and modern terminology in terms of legal points and so on. You can check. There was a paper, Greenwich. There's someone else that I forget. The other author for reformulating Peloton's theory in terms of legal points. The results of a number of Peloton's theorems. So for let's say relation of returns results to in the language of legal points, or translation, let's say. So again, essentially, Pelletan's idea was that these gammas should come from a set of should come from differential equations on your manifold. So we fix now X to be our compact Riemann surface, compact connected Riemann surface, again just for fitting this with for fitting everything in the context, right? We know that the complex structure is given as an equivalence class of homomorphic atlases, right? So the complex structure is given as is equivalence class of homomorphic atlases, right? Let's say 2 alpha z alpha. Right? So your function is Q alpha beta are homomorphic. Now, the equivalence is the union of two atlases, two homomorphic atlases, again, a homomorphic atlas. Right? So, in this context, we're going to consider gamma. I'll use it in a couple of places. So, gamma would be the locally defined complex analytic local homomorphisms. So, complex analytic. Homomorphisms in diff x, diff log x, right? So essentially our condition here is that the derivative is non-zero. Our phi alpha beta, right, the gluing function of your atlas are elements of this pseudo group. So one idea, essentially what the idea that Granik is using is that you can be producing new structures on your Riemann surface by looking at some smaller pseudo groups that are compatible with the complex structure. So so consider let's say smaller. I mean, consider sub pseudo groups of gamma if you want. Consider smaller pseudo groups. Let's say inside gamma to get new structures on X. Right? In other words, the idea would be restrict the gluing data to a smaller class and choose gluing functions that are of some special nature. And well, we'll be using essentially one of these. In fact, two of them that come naturally, and one is a special case of the other. So Gagnon calls these F1 and F2. So we introduce two differential operators. set, which are very simple, theta 1 and theta 2. Theta 1 of my function would be essentially the logarithmic derivative of the, well, the f double, so z over f times. Since we'll be working with functions that are in gamma, the derivative, so these f's will be our phi alpha beta, so we won't be having trouble with dividing by this. And theta 2 of f of z would be essentially the Schwarzian derivative of f, right? We have a number of ways of writing it, right? So we can think of it as 2f prime f triple minus 3f prime double squared divided by 2 f prime squared, right? Of z. So let's introduce. Let's fix these. By the way, again, of course, there are multiple ways of writing the Schwarzian derivatives, right? So you could think of this theta 2 actually in terms of theta 1, right? So you can think of the theta 2 as theta 1 of f prime minus a half theta 1 of f squared. If you were to spread the Schwarzian as the logarithmic derivative of f prime, the derivative of that minus a half of the square. So let's see. So the idea would be to pass through or to consider on the Riemann surface atlases where the transition functions are annihilated by these theta 1 and theta 2 respectively, right? We don't know whether such a thing exists, right? This was done, so Gunning had a long paper called Special Coordinate Couplings of Riemann Surfaces. Also, he had in his book on Riemann surfaces, he essentially devoted a chapter on, actually almost maybe a third of the book to these structures. Okay, so to see that we'll actually get this Euler group, and for various other technical reasons, we'll formulate a lemma that we used a number of times. So let's say we're fixing gamma to be the log of numerism. So doing the functions with derivatives are homomorphic ones. So let's pick f and g. So f and g in gamma. Let's say the so f is from u to v, g is from u to w, and right. So the image of f is in the domain of g. Then there will be a statement about the behavior of these theta 1 and theta 2 with respect to composition. So these two operators have special property with respect to composition. Essentially, it's a kind of co-cycle condition that comes out of this. So let's derive H for the composition, G after F, and W for F of Z. Just to make things a little bit more palatable. So then theta R, so R would be 1 or 2 of the composition of Z. Well, it's going to be theta R of G of W times F prime of Z to the power of R. So it will be either 1 for this operator or 2 for the other one, plus just theta R F of Z. Right? So this is R is 1 and 2. So this is essentially the chain rule. So for the, let's say for the Schwarz derivative, this is telling you that the Schwarz derivative for composition, right, is the Schwarz derivative of the outside function times f prime squared plus the Schwarz derivative of f. Right.
Peter?
Yes.
When we define the theta 1 and theta 2, it seems depends on the choice of coordinates.
So this is, yeah, so we're making a local statement. Yeah, well, so far we're working on an open in C, right? So if you want, these could be, I mean, yeah, this is purely local statement. So indeed, so when you change the chart, yeah, when you try to globalize, when you change the chart, yeah, of course there will be a fudge factor exactly because of this. So this is not. I'm not saying this is invariant under diffeomorphisms or anything like that, right?
Okay. So we take the complex plane as a model space, and now we consider the gamma on this model space.
Right. Right. So this is, I mean, the way to check it. I don't think it's. I mean, could go through, but this is actually the chain rule. This is the chain rule for theta 1 and theta 2. So you see what the chain rule gives you for f prime, you see what the chain rule gives you for f double and f triple, and you plug in. I mean, what is actually the frequency? Do you, I mean, I don't know if people are interested in going through it. I mean, it's, I think everybody can do it, but it's, I mean, again, you write down the chain rule for f prime, for f double and f triple, and then substitute in the expression, and you see that's what's left over. So again, if I mean, it's okay.
Exercise for the reader.
I mean, it's a half a page of calculation with computing successive derivatives, right? All right. So what we do now is we consider two on our regular surface. We consider two sub pseudo groups, right? So we consider inside gamma defined by so these are local homomorphisms, complex analytic. So these are F's V convex analytic local monotonisms such that delta R is 0. Right? So these are either the ones that are annihilated by delta 1 or by delta 2. So what is the, so you see if delta 1 of F is 0, right, immediately delta 2 is 0. So one of these is contained in the other, right, F1. We have that F1 is contained in gamma. Right? If the derivative of F time is 0, then this is gone and this is gone. Now, in principle, we can ask why we consider these special differential operators. So, in fact, Cartan proved that these are the only pseudogroups arising from differential equations. So, right, so so this is Lee Cartan, right? So Lee Cartan proved these are the only pseudogroups in dimension 1, right, on the surface. So rising from so this is 1904. So what's in there? Right? What are the functions? And so first of all, just looking immediately at F1, right? We want F double over F prime to be 0, so F double should be 0. So this family F1 just consists of affine maps. So with affine linear maps, right? So now what is in F2? So F2 consists of actually a fractional linear for Laplace transformations. Right? So this is fractional linear transformations. So the way you can see this is to rewrite the Schwarzian derivatives in terms of the second derivative of the root, or minus the root.
In the terms of?
So if in terms of, I mean, on a, yeah, I'm slightly abusing this passage here because we're working with the local picture. So first, so if you just saying if you just work first with open sets, if your gamma consists of local analytical homomorphisms of C or P1 if you wish, right? And you look at the function defined there. So we're assuming the fixed choice of the local coordinate. Then, well, a function would be annihilated by this differential operator if and only if it's a fractional linear transformation. Right. So yeah, I should be saying these are in C. So again, where is this coming from? So the idea is whether I theta 2 okay, as fz is so you look at the f prime of z minus 1/2. The second derivative of this minus 2 f prime. So if you again, this is it's a direct calculation. You write the computer. This is a third order operator. This is another one that we're checking. We're claiming they're the same. Right? So differentiate f prime to minus 1/2. Yeah, we're working with Markov homomorphisms, complex analytics. So the derivative is never 0. So we don't have a problem with vanishing denominators. So once you do this, again, anyone wants to put, we can work it out. Okay, this is the chain rule. So once we do this, right, we see that if theta 2 is 0, essentially we know what the f prime will be. So,
sorry.
Yeah.
So we fix a square root, or it doesn't matter.
I mean, this is a local discussion. It doesn't matter.
Oh, okay.
Yes, I
It
mean,
doesn't
work
matter.
with the whole pseudo group, and yeah, right. So if you, I mean, so if theta 2 is 0, right? We see that. Z is 0, and only if well, if z is at the form over c equals d squared, right? This is, I mean, this expression f prime minus 1/2 is affine linear, right? So so this is f prime, right? So so then you integrate this once more, and you end up with a fractional linear transformation. Now the condition to have a local homomorphism is that this is equal. Right? So if you so your collection of these locally defined maps that are annihilated by the operator, by the respective differential operators. Well, one is the affine linear transformations, and the other is the fractional linear. Right? And essentially, Cardano is saying that there are no others coming from differential equation. Okay. All right. So you can now say, well, I have my Riemann surface. It's defined by this class of homomorphic atlases. Now, what if I ask for an additional structure, which would be an atlas whose transition functions are in this pseudo group instead of just arbitrary diffeomorphisms. Right? So that would be called a projective structure or an affine structure, or if we're using this notation, it would be an F1 or an F2 structure. So. Yes, right. So let's say if we want to split it in two, right? We can say so on let's say FR atlas, right? On X is or is a homomorphic atlas. Let's say Q alpha Z alpha, such that transition functions Q alpha beta belong to and an FR. So again, R is 1 and 2. Usually we just say affine or projective, but okay, we're keeping the common sort of nomenclature for the moment, right? And an FI structure, in other words, projective or affine structure. So FI structure would be an equivalence class of such atlases. Again, the equivalence is the union of the atlases within such an atlas. So we call it, we use also affine or projective. Structure for F1 respectively, right? So practically what is this? This is an atlas on which the transition functions are either Möbius transformations or affine linear, affine linear transformations. Right? We don't know whether such a thing exists if we give me the Riemann surface, right? But it's clear. First of all, it's clear that we, let's say, if we have an affine structure, it determines a projective one. So the inclusions are compatible with the inclusions of F1 into F2 are compatible with the equivalence classes, right? So every affine linear, every affine structure is a projective one, right? And we are also using these structures are compatible with X. So compatible with the complex structure on X, right? So on F1 structure on X is a F2. If an S2 structure on X, right, is a complex structure on X. But this is again, this is an extra data. It's not a restriction on the. We don't know whether each Riemann surface would admit such a structure, but if it does, so if such a structure exists, this structure would be an extra data on the surface. It's not. I mean, it's a special atlas, but this choice of special atlas will make extra data. So that was a No. This is provided it exists. In principle, actually, you could start. You could look for affine or projective structures that are not necessarily compatible with your complex structure. So those people call these like real projective structure. In other words, if I have an atlas whose functions are modulus transformations, okay, then I have a complex atlas. So you could say I have some structure, whatever it is. I'm looking for another atlas. It may or may not be compatible with my own. So in principle, there are many more real projective structures than complex ones. So we're looking at ones that are compatible with the complex structure. Okay. So these I understand that this discussion is very local, complex, analytic. So we can't see any geometry behind it yet. So I'll keep it like that at least for today, and then hopefully tomorrow we'll start looking actually at these objects in terms of bundles and connections.
Maybe I can ask a question. Can such atlases be constructed using universal covers? Say.
So you could, yeah, that's the thing. You could actually, that's one argument that. Because you have, that's another thing to do, right? That's another natural thing to do. You have it on the universal cover, and then you can try to get it from there. So in principle, there are many more. I mean, but that's so the uniformization. What I was saying is that actually we can use uniformization to produce the structures. So there is actually we have a non-canonical choice actually of a projective structure on each Riemann surface, right? And for genus 1, it's I mean for P1, right? For P1 we have the standard atlas with the stereographic projection. The transition functions 1 over z. It's fractional linear. For genus 1 we have it because we glue by affine transformations. Again, the usual choice of atlas that you put on it. For a higher genus, you could try to get these by uniformization, using that you have the upper half plane as a cover. So uniformization would give actually one choice of such structure. There are actually as many of them as there's a 3G minus 3 dimensional space of these. So every quadratic differential is giving you one of these structures. So it's this data, whatever it is, it's an affine space over the set of quadratic differential.
But for a fixed complex structure?
Yes, sure. Right.
But this gives at least an existence.
This gives an existence, yeah, sure. Right. That was, so we can see it already now that we have existence. Right? If you want to tackle the local question, because this question also makes sense locally, you can ask it on an open Riemann surface, right? You could ask the same question. So let me try to say a few words how we can actually describe this in terms of in Czech terms, right? words about getting some kind of technological description of these. By the way, already before we start, I'm going to go in the direction of describing these objects in terms of check covers and but even let's fix an atlas for simplicity. So for the moment, I'm not requiring that it's compatible with class 1 ADS structures. Like this, or X and or whatever. So I'm gonna write KX for the canonical. X. Now, if you know that if you think of the canonical bundle as an element of H1, the class of the canonical bundle as an element of H1 of all star, right? The transition functions are the coefficient, the derivatives of these z beta dz alpha. Right? So the class, let's say this is a good cover. Right? So all the intersections are compatible, so that you can compute cohomology if you wish. Right? So we can think of this whole star. Right? So this class is represented by I'm going to write kappa alpha beta, right? At the point which would be dz beta dz alpha. And so I'm thinking this is a class in H1. Right. So you want the alpha beta we just said few times. So just I'm trying to fit it in the least space possible. Phi alpha beta prime at the point to the minus first, right? This is dz beta dz alpha. So now, essentially, the chain rule that we derived will allow us to think of the F1 or F2 structure as a certain cocycle. So we're going to hook up a cycle that would consist of the derivatives with respect to theta 1 or theta 2 of these phi alpha beta. Right, so consider the functions theta r of phi alpha beta. Right, so I'll be thinking of these as functions in defined on C, right? So let's say this is equal at the point, right? So these are elements in z beta of who is that? So I'm going to say to denote as usual u alpha beta to be u alpha intersection z beta. Right? So you take your atlas, you take your transition functions, and you apply the differential to the differential operator theta r this phi alpha beta. Now, if you use the lemma and see what happens when you switch from z beta to z gamma, for example, these actually determine one per cycle with coefficients in the power of the canonical. Right? So this determines. There is no, this extra structure is not present here, right? We're just picking Riemann surface, we pick an atlas on it, right? So there is no projective structure inside. So we pick an atlas, the atlas has some transition functions, and we hit the transition functions with the differential operator, right? So these determine some CR, that we call them, so one for each of these. So CR in the check C1, a section of Q alpha beta k to the power, right? I'm missing my subscripts, right? So in the lemma, right, by the chain we had a coefficient of the derivative showing up, which was either 1 or 2. So these CRs, right, determine some one chains, right, of the canonical bundle with respect to the cover. Right? So this is a one of in other words, I mean, what am I saying? So, in other words, CR alpha beta. If I'm staying on the open alpha beta, but I'm looking at I'm using also a point that's in the intersection of the alpha beta with T gamma. So think this is the gamma of T. This is what this is kappa beta gamma. So gamma beta to the R, the point CR alpha beta of P. Right, the powers of the canonical are given by powers of R. Now, what happens if we patch, right? If we try to patch. So, if we look at an open the alpha beta gamma, we see the following. Again, I'm using the lemma, the chain rule, a number of times. So if I look at theta R of P alpha beta, let's say of Z gamma. Now I can write this as theta R P alpha beta of Z beta times, well, of Z beta times P prime beta gamma to the alpha power plus there was the second piece of the chain rule of the lemma theta R beta gamma just delete this. And move everything to the coordinate z gamma, you'll get exactly that C1 is actually a cocycle, right? So this means theta I, alpha beta z gamma is is theta I. So, I mean, we're getting that sigma I alpha beta minus sigma I alpha gamma plus sigma I alpha gamma is 0. In other words, our class CI is a one cocycle. In sigma I is in C1 Q with coefficients in the rth power of the canonical. And so this is again, this is something that holds for any atoms. That you pick the atoms, you apply these differential operators to the transition functions, and well, you get yourself a one cocycle with coefficients in kx or in kx squared. Now, you can ask, is it a coboundary? Well, isn't it a coboundary, right? So we immediately have some conditions. For example, let's put this in the question. Is this sigma I, and the two of them are coboundary, right? Is there some H, we can call this H alpha, in C0 u to the I, so H is here, right? Such that sigma I alpha beta is H alpha minus H beta, right? This is question. So there is a Gaussian code calls these projective or respectively affine connections. So every such cocycle. There's a bit of clash. That a posteriori, that's not really a clash, but so we don't see any connections here in the differential metric or algebra geometric sense so far. Right? So running goes such an H, such a class, right? Affine if R is 1 for a projective connection. It's easy. I have to look it up in a bit. Yeah, so it's easy to see some cases in which this cocycle will be automatically trivial, right? For example, if you have an affine open or Stein open, if you just look at one of an open level surface, this H1, the H1 will be trivial, so that will be automatically the case. If the genus, by applying by doing enough, right? If the genus is greater than is at least 2, this will be automatically 0 as well. Right? So now, just to get at the place in which we can wrap it up, the statement of the key theorem that Ganek formulates is that there's a one-to-one correspondence between these zero co-cycles and the projective or respectively affine structures on the curve. So there's natural one-to-one correspondence between projective or affine structures on X and projective or respectively affine connections. Connections in this sense, right? In the above sense. So essentially the idea is you start with an atlas, you compute this class. Let's say if you have one of these, zero check cycles, how do you get a projective structure? Well, you try to modify the atlas by composing with some functions. You try to modify the atlas so that the Schwarzian derivative becomes 0. So the question boils down to actually some differential equation admitting local solutions. So from each such class, you get your projective structure. From each projective structure, you get such class. So we get at least we can answer now lots of some of the classification questions. Right? It's clear that on an open surface, this H1, the respective H1 will be 0, so this I want to tell you, so there will be a projective structure on a curve. So we can answer it without appealing to uniformization, right? On a curve of genus at least 2, there will be one such structure, and actually we can see that if I have 2 of these, the difference of them will be a global section of k squared or a global section of k. So it would be either a usual differential or a quadratic differential for the case of projective structure. So so we'll have to wrap it up. So next, I'll try to maybe say a bit more about the proof of this tomorrow, and then we'll pass to actually looking at these objects in terms of bundles and connections. It's clear that actually, if you think of it, that there should be a flat connection somewhere here, because the Möbius transformations that give the transition functions, if we have a projective structure, are constant Möbius transformations. So we have some element of H1 of PGL2. So H1 of the constant sheaf PGL2. So there is some flat PGL2 bundle behind a projective structure. So it's kind of clear that there should be some flat connection in the classical sense. And I'll discuss actually what is the correspondence between this data and the data for bundle with a flag with a very special reduction to a Borel. So the idea is that the PGL will be reduced to a Borel subgroup, but the reduction would have a very special property. So there will be a non-degeneracy property of the section that gives the reduction. And So I try to start today classically, and so we'll see more of the geometry tomorrow. So yeah, so let's I'll stop here since we have to stick to the schedule. So.
Okay.